Welcome to Mass Transfer Operations lecture series.
Let's recall a few points. We discussed about mass flux and molar flux in the last class. Both are used to quantify mass transfer. The units are kilogram per meter square second or kilomole per meter square second. And I also discussed that both mass flux and molar flux can also be expressed relative to mass average velocity and molar average velocity. So here what is Ja is the mass molar flux relative to molar average velocity, and Ia is the molar flux relative to mass average velocity. We will discuss the basic law of diffusion called Fick's law. For that, like always, let us assume the rectangular tube in which molecules A and B are present, which are trying to diffuse inside the vessel. So, according to Fick's law, the molar flux of a species relative to an observer moving with molar average velocity is proportional to concentration gradient of the species. So I said the driving force for mass transfer is concentration difference. So wherever there is concentration difference, the molecule will try to diffuse. According to Fick's law, the molar flux is directly proportional to concentration gradient. It is not clear here. Actually, it is Ja, the molar flux relative to molar average velocity is proportional to concentration gradient. And if we remove the concentration gradient, we can write Ja is equal to minus dAb into dCA by dz, where dAb is the proportionality constant called the diffusion coefficient or diffusivity of A in the mixture of A and B. This law is analogous to Fourier's law of heat conduction. According to Fourier's law, the heat flux is proportional to temperature gradient. Similarly, here the molar flux is proportional to concentration gradient, because here concentration gradient is the driving force, and in heat transfer temperature gradient or temperature difference is the driving force. So, and in order to remove the proportionality constant, we introduced a term DAB, and DAB is called diffusion coefficient or diffusivity of A in a mixture of B, because it is the factor that determines the rate at which molecules are diffusing. If the value of DAB is high, it means diffusion will be more. If DAB is high, value of DAB is low, diffusion will be less, irrespective of the concentration gradient. So if I say similarly, we can write JB is equal to dBA into dCA by dz, where dBA means proper diffusion coefficient for the diffusion of B in a mixture of A and B. So this conversion should be followed. DAB means diffusion of A in a mixture of A and B. So you are already aware of the unit of J. It is kilomole per meter square second, and we know the unit of concentration gradient. It is kilomole per meter raised to 4, because concentration unit is kilomole per meter cube into distance will give you meter raised to 4. So accordingly, the unit of diffusion coefficient DAB will be meters per second. Now the Fick's law gives an expression for molar flux relative to molar average velocity. Now, based on this law, let us try to find an expression for Na, that is molar average velocity with respect to a stationary observer. So, in the last class, we discussed the difference between Na and Ja. So, I hope you are aware of it. So, let us try to develop an expression for Na based on Fick's law. So we will start with what we already know. Here we know molar average velocity U is equal to CAUA plus CBUB by C. We learned this last class. But we know Ca into Ua is equal to Na. Na is equal to Ca into Ua. So I can write instead of CAUA Na and CBUB Nb. So U is equal to 1 by C into Na plus Nb. So in last class we also discussed an expression for molar flux relative to molar average velocity Ja, which is equal to Ca into Ua minus U. You may refer to this if you have any doubt regarding this. This was discussed in detail in last class. So Ga is equal to molar flux Ja is equal to Ca into Ua minus U. From Fick's law, molar flux Ja is equal to dA minus dAb into dCa by dZ. I didn't explain one thing. See, why did we use a minus sign here? It is because the flux is a positive quantity. It is taken as a positive quantity by convection because it is moving from a region of higher concentration to a region of um, lower concentration. But here this quantity dCa by dZ is a negative one because why? Ca is molecules are moving from higher concentration to a lower concentration, and Z is increasing. So one quantity is decreasing and other is increasing. So the derivative will have a negative value. So in order to get a positive quantity, in order to make J a positive quantity, we are using a negative sign here. Okay, let's get back. So we have two equations, 1 and 2. Let's equate these two. So minus dAb, dCa by dZ is equal to Ca into Ua minus U. Let's multiply Ca into Ua minus Ca into U. Now, CaUa minus Ca into U. What is Ua? What is U? Molar average velocity. I've written somewhere here. U is equal to 1 by C into Na plus Nb. So let's replace U with Na plus Nb by C. And again we can take C outside. So this equation like minus dAb dCa by dZ is equal to Na minus Ca by C into Na plus Nb. Here Ca into Ua is equal to Na. This also we learned. So replace CaUa with Na. Now I am going to rearrange this equation. Here Na is equal to Ca by C into Na plus Nb. Na is equal to Ca by C into Na plus Nb minus dAb into dCa by dZ. I rearrange this equation because I need to find an expression for Na. So what we got now is Na, the molar flux of A in a binary mixture with respect to a stationary observer based on Fick's law. Na is equal to Ca by C into Na plus Nb minus dAb into dCa by dZ. Okay, so let us have a look at the equation for Na. Here we can divide this into two parts. So the first part is Na plus Nb into Ca by C, and other is minus dAb into dCa by dZ. This quantity represents the molar flux relative to molar average velocity, and I can say according to Fick's law this represents molecular diffusion, and this quantity here represents bulk flow. Why is it like this? Because see, if you have a look at the motion of molecules, these molecules will be in constant motion, and I have said in the previous class the diffusion process takes place only till it collide with a nearby molecule. Let's suppose a molecule A is moving in this direction. Immediately it will collide with another molecule which is present nearby. So once it collide with another molecule, it is exerting a force into that molecule, and immediately a bulk that movement will be contributed to the bulk flow of the molecules. So diffusion will take place only if there are no collisions. Before the collision, the process can be called as diffusion, and after the collision, it is actually bulk flow. And we also discussed diffusion of before the diffusion of A molecules, the velocity of the component A should be greater than the molar average velocity of the mixture. So if you feel confused, forget about all these complications. Only thing is we got an expression for Na, the molar flux with molar flux of A with respect to a stationary observer. That means with respect to a person standing outside and looking at the process. The unit is kilomole per meter square second, which is equal to Na plus Nb into Ca by C minus Dab into Dca by Dz. So this is the expression for molar flux Na. Let's see its significance. Suppose the value of Ca is very small. Then what will happen? This quantity Ca by Ca will can be approximated to 0. So now Na is equal to minus Dab dCa by dZ. But what is this quantity called? It is J. That is molar flux relative to molar average velocity. So that means when the concentration of A is very small, diffusion is predominant because small amount of A is present, large volume is available, so molecules are free to diffuse. Collisions will be less, so the entire transfer will be through diffusion. So I hope now it is clear. Now let's introduce a term known as diffusion velocity. So I said diffusing molecules moves with a velocity greater than the molar average velocity. Then only it will actually diffuse. Otherwise, it will be trapped inside the molecule. Means inside the mixture. If it needs to diffuse out of the mixture, it should have a velocity greater than the molar average velocity. So the relative velocity of a component A with respect to molar average velocity U is called diffusion velocity. So this is simply the difference between the molar average velocity and the velocity of the component. So diffusion velocity, that means the velocity at which the molecules are diffusing, is equal to UA minus U. This is just like, let's say you are moving in a car and another car is trying to overtake you. The car can overtake you only if it is have a velocity greater than your car's velocity, and the difference in the two velocities will be the actual velocity experienced by you, and that is equivalent to diffusion velocity. So VAD, that is how we represent diffusion velocity, is equal to UA minus U. But we know JA, molar flux, is equal to CA into UA minus U. We discussed this in the last class. So from this I can say UA minus U is equal to JA by CA. And what is JA? Minus DAB into DCA by DZ. So VA, relative velocity or diffusion velocity, is equal to minus DAB by CA into DCA by DZ. So now let us discuss molecular diffusion in gases. So we are going to modify this expression, because in this expression the terms are represented as concentration. See here. But I said if it is in gas phase, for gaseous mixture, we will represent concentration as ratio of partial pressure and total pressure. Let's just try to write an expression for molecular diffusion in gases. So molar flux Na for a component in gaseous mixture. Let us assume the gaseous mixture behaves ideally. So we can write Pa into V is equal to nRT. I wrote like this because the general expression is PV into nRT. So for component A, Pa into V is equal to nRT. If we divide V on both sides, we will get Pa is equal to N by V into RT, where N by V is equal to N is the number of moles and V is the total volume. So N by V is equal to Ca. So P is equal to Ca into RT. So from this we can write Ca is equal to Pa by RT. Total concentration C is equal to P by RT. Since Ca is equal to Pa by Rt, if I differentiate this with respect to Ca, I'll get dCa is equal to dPa by Rt. So let's substitute for Ca, C and dCa, and we'll obtain an equation for Na for a gaseous mixture in Na plus, which is equal to Na plus Nb Pa by P minus Da by Rt, Dab by Rt, dPa by dZ. We'll use this to solve problems and it will be clear. Okay, now let us prove that mutual diffusities of A and B, DAB and DBA are equal for an ideal gas mixture. So if the gas mixture is ideal, it should be the DBA and DAB, the diffusities of A and B should be equal. Let us try to prove that. So from Fick's law we have molar flux J is equal to minus dAb into dCa by dZ. So molar flux with respect to molar flux of B, that means the flux with which B is moving, is equal to minus dAb into dCb by dZ. So the system that I've assumed is an ideal gas mixture of A and B in a vessel of non-volume. So let us write the expressions for Na, that means the molar flux for a molar flux seen by an observer standing outside who is stationary. So Na is equal to Na plus Nb Ca by C minus Dab dCa by dZ. Similarly, we can write the molar flux Nb is equal to Na plus Nb into Cb by C minus dBa into dCb by dZ. So add these two. So 1 plus 2 will give you Na plus Nb is equal to Na plus Nb into Ca by C plus Na plus Nb into Cb by C minus Dab dCa by dZ minus dBa dCb by dZ. So Na plus Nb is common here. We can take that out and we'll get an expression like this. But we already know Ca plus Cb by C. But we know Ca plus Cb is equal to C. So this term will become equal to 1, and now we have only Na plus Nb here, so these Na plus Nb cancels off, and what is left over is minus Dab dCa by dZ and minus dBa dCb by dZ. Let's take 1 to LHS and we'll get Dab dCa by dZ is equal to minus dBa dCb by dZ. So if dCa by dZ is equal to minus dCb by dZ, we can say dAb is equal to dAb. Let us assume that in this vessel the concentration gradient for both A and B are equal and opposite. So in that case, I can say the diffusion coefficient of diffusion coefficient dAb is equal for a component A in the mixture is equal to diffusion coefficient of B dBA in the same mixture.